All right. Questions? Any question?
I wanted to learn about like quarks and baryons and mesons and
Oh, standard model, right?
yeah,
Meson.
the fundamental particles.
Yes, fundamental model. But that's fundamental model just for the subatomic particle, right?
Mm-hmm.
And it would be too tiresome if you just want to build, say, a molecule, right?
Yeah.
It would take ages to build, a protein by use quarks, right?
Mm-hmm.
So all these so-called fundamental particle are can be used to build the observed particle at high energy level, so not ordinary stable nuclei, but under the extremely high energy that a human can generate it at the moment.
Mm-hmm.
So people argue that probably we can, if we go higher energy, perhaps no more phenomena, more new form particle can be observed. But that is something totally different from this original idea. So the standard model, if I just how many type of standard model do you know apart from this individual particle? You mentioned a few, right? Quarks,
Mm-hmm.
muon. Did you how much?
Yeah.
And pion, right? So how do we put this
Baryons
into
and mesons.
categories? You got look up and down. We got up and down. Okay, we have several
Mm-hmm.
particles. We have a top and bottom, right?
Mm-hmm.
Top and bottom. Anything else? And the charm and the strange, right?
Mm-hmm.
The probably is not the order they give you, but just this is 6 quarks, right? 6 quarks.
Yeah.
So each quarks, how do we describe the quark? For example, so they are all called quarks, right?
Mm-hmm.
How can we describe them? How can we define this quark? For example, how do we divide U? So what is the charge of U? For example, let's just put it here. So what is the electric charge in E? And what is the spin? And what is the mass, EMeV, divided by C squared? Can you tell me, do you know these properties? So that's how do we define particles in just a few numbers? Just like, of course, we define. So in the government fires, every person is defined by several numbers, right?
Mm-hmm.
Age and anything else, names, first name, second name, right?
Yeah.
And male, female, and that's it. So that's how we can use just a few numbers to define a particle.
Mm-hmm.
In other particles, the charge is very strange. It's 1/3. Positive, negative. Double check that. 1/3. Stability. Can you check your table? It's
I
positive.
think it is like that.
Sorry.
I think it is like that.
It's
Something like that.
positive or not negative.
Um.
It's very strange because it is a fraction of the electron charge. E is the electric charge, right?
Mm-hmm.
Should I say this? This is the first property. Yeah, this is you're talking about standard model today. So basically, what should I write it here is you have electric charge. Charge we can use Q, right? But
Mm-hmm.
unit is E, so that's how we denote that. Is that 1/3 or negative 1/3?
I can't find it.
Ah, I can find it for you then. I got a table for this for this particle model here. Okay, I got everything out. So I got this. You see, I got a postcard. Can you see this postcard side table? I got everything you want. So basically, yes, I am almost right. This proper notation. So I just checked that. I have used with my glasses. If the upper cortical, they have 2.3 meager. That's presumably that is a mass. That's right. That's right. The charge The charge is two-third. Is two-third. I'm wrong. Can you see? And can't remember. We can't remember that everything. We just write down here. So this number is very strange. Is two-third. So it is a fraction of electron charge, right? This is a 2/3. Now, how about a spin? Can you guess what is this S for spin? Have you heard of spin?
No, is it negative, positive?
No. It's just half. It's half. How about the mass? Oh, that is a 2.3. Okay, that's the meager. That just represents the mass. So that if you know these two numbers, and then we can almost know the quarks. For the d quark, let me see. D quark is 1/3, but negative. You can see. And the spin is the same. I will tell you why. The spin is the same. Can you see? Similarly, I give another group is called. Do you remember? Apart from the quark, there are another 6 particles called the lepton. Lepton. We have leptons. Leptons are the category of these 6 particles. One of them is very familiar. It's called electron. You see. Another is a muon. This is a neutrino electron. You can see sub E is corresponding. At the beginning, when we study nuclear decay, we know that apart from electron, they also have the invisible particle called neutrino, right? So this is neutrino. So basically, these two categories. This category 1 is electron. We know electron in chemistry, right? Electron is one of the 3 fundamental particles in chemistry.
Yeah.
What are other 2 in chemistry? What are the fundamental particles in chemistry?
Protons and neutrons.
Yes, that's right. That's all. Okay. We don't need we don't need a standard model, right? we only need the Mendeleev's a periodic table. You agree? However, if you go to this neutrino, neutrino. That is very strange particle, right? So that's E, and mu is called nu, Greek letter nu. And later on, people realize that we can have something similar. Some particles are similar to electron. Charged particles called mu, and tau. Okay. So correspondingly, they also have 3 corresponding neutrino. Can you see? They are all neutrino, but different type. Okay. So quark plus neutrino, and this category is called. Do you know what is? Do you know what is this category called in standard model? All of them. I take it. I give example. For example, how can we build the same table for electron? You see, electron. Oh, by the way, can you see proton and neutron here in this 12 particle? Can you see neutron and proton? No, you can't see, right?
Yeah.
Because both proton and neutron are considered as they are made by quarks. Okay. So in the standard model, the proton and neutron are no longer the elements, but is a composite particle. This idea is quite different. It's quite new, right? In chemistry, we take it for granted that we can build everything, every chemical, every material by just 3 types of particles. If we continue, so can you tell me what is the charge of electron? Continue in the unit of E. What is electron?
-1.
Yes, that's right. How about spin? Can you guess?
1.
Half. Can you see? Because all of them called the fermion. Can you see? Can you write down here? Or even the neutrino. Neutrino got a spin. It's also the half. Yes, neutrino also. Can you put a neutrino here? How about the charge of a neutrino, by the way?
0.
So, but it got half spin, all right?
Mm-hmm.
And then in addition, of course, it's got mass. So for the electron, and the mass is less than 2.2. That is a unit for this MeV divided C square. Do you know the MeV is energy? Can you see?
Mm-hmm.
The MeV is unit of energy. This is called the unit. The energy can be joule, right?
Mm-hmm.
And energy can also, when we study the nuclear physics and subatomic physics, we prefer use MeV. M means bigger, not bigger, EV, you see?
Mm-hmm.
Of course, according to Einstein, the E is equal to mass multiplied C squared. You see that?
Yeah.
So therefore, the mass unit in the international system is a kilogram, right?
Mm-hmm.
However, in nuclear physics, people and also in particle physics, subatomic particle study, we prefer use this unit. That's MeV divided by C squared, or simply write as M, right?
Mm-hmm.
So that is about the unit. So you can see that the quark is heavier. Okay, quark is much heavier than electron. But for the neutrino, what is the mass of neutrino? Do you know? Neutrino. Does it have mass at all? Does neutrino have mass at all?
No.
No. Put a question mark. So basically, neutrino was the first denote appear when we studied this nuclear reaction or nuclear decay. This is called beta decay, right?
Mm-hmm.
You remember this formula, this reaction, nuclear reaction. This become proton, right?
Mm-hmm.
And plus what? Can you finish this diagram? Can you finish this decay equation? So they are related. These phenomena are related to that will tell you the mass of neutrino. In order to make the charge, can you see this notation? This is a mass number. This is atomic number, or this number of the proton. And do you agree? This is nuclear notation. That's right. We must put a negative electron here. That's right. And this is very close to 0. And if you want to put additional charge here, like neutrino, and by the way, if you put this tilde, we call the tilde at top, it's called anti-neutrino. Okay, so this is anti-neutrino. So this is anti-neutrino. Can you see? Have you heard anti-neutrino?
Mm-hmm.
Yeah, we do. That's how we saw this equation here. Nuclear decay, beta decay, neutrino. Neutrino, anti-neutrino. Similarly, so this is so we got neutrino and anti-neutrino. You see, it's called neutrino tilde. Can you see?
Mm-hmm.
And also we got electron. We also got anti-electron, but anti-electron has a proper name. Do you remember what is electron? Positive. Something starts with a positive.
Positron.
Yes, positron. You see. So the positron is actually should be called as anti-electron. You see.
Mm-hmm.
So that is something totally new from chemistry. Anti-electron. Because in chemistry we only study the material or mass, the matter, right?
Mm-hmm.
But in nuclear physics, but in the subatomic physics, this group, of course, that will make up a matter, right? So all of them put it together, they will make the matter. So they will make the matter we know in chemistry, right?
Mm-hmm.
And also their anti-particle, when they put them together, they can make an antimatter. So if you want to know, if you want to accept the idea in a standard model, we have accept that our world is the natural world, the universe must be made by matter and antimatter. So it's getting more complicated, right?
Mm-hmm.
So that is idea. Okay, there are many strange ideas in the standard model. All right. So that is yeah. Well, this is part of the idea in the antimatter. Sorry, in the standard model. Okay, standard model. Yeah, I've teach standard model several times. This time I just change the order. So basically, this group, remember, all of them, all of these how to make 6 plus 6, 12 particle, plus their antimatter. How many altogether? Plus their antimatter. You have imagined that there's another table which lists all their antimatter. You tilde, can you
18.
see? Yes, that's fair.
Mm-hmm.
4 times 6. 6 times 4.
Why would it be 4? Oh, for both of them antimatter?
So sorry, 6 times 6, no, yeah, 12 times, yeah, you're right. 12 plus 12. 24, right? Did you say 24?
I said 18.
How come we are 18? Each thing easy, you just count. We have up.
Oh, well, these have antimatter too.
Oh
Quarks
yes,
as well.
anti-quarks. As yes, I
Yeah,
didn't
then-
write down here. I didn't write down. They have anti-quarks. Yes, so that is that's new idea in physics. It's called anti-quarks. If you have quark, they have anti-quarks.
Mm-hmm.
Yes, this is a quarks. So how do we denote that? We put the tilde here. This is up.
Mm-hmm.
That is anti-quark. You see,
Mm-hmm.
so the anti-quark can be built in the notation. Can be so you can imagine there are 12 plus 12. So altogether there are 25. You see, 24, right? This category called the fermion. Have you heard of fermion?
No.
Fermion. So fermion. So this is something you need to know, that when we study a standard model, we are dealing with so-called particle. Okay? This particle may not be the same property, same nature of the we familiar with, but we call it particle, right?
Mm-hmm.
And these particles, all of particle, if you say, if in English, when we build the word for particle, we all prefer to use the Latin on as a, like, the proton, neutron, can you see?
Mm-hmm.
Except neutrino, okay? Neutrino is slightly different. And because at the beginning, people don't think it's a particle. It's just something who carry certain amount of the spin away, right?
Mm-hmm.
Where are we? Oh, here. So I just highlight. So you see, when we start the new, when we study these subatomic particles, we can always see the on. I pick up wrong. Moment. One moment, I just change the color slightly. You see the on here, can you see? Can you see the positron? It's not a train, but the positron, can you see? On. They all start from the on, can you see?
Mm-hmm.
And quark is something where people choose the word without much concern. They just in the fancy name, right? And you can find many cases where the particle, any particle, they always with on. Okay.
Mm-hmm.
So when you say the on, you know it's a particle. Although for quark it's not on, but it still is considered as a particle. By the way, these particles are no longer necessarily physical particles. They are mathematical elements in order to build a complicated particle.
Mm-hmm.
So what I'm trying to highlight is here. You see, can you say electron on? Can you see on here? Lepton, can lepton on? Can you see? There are many examples. So all of this category is called the fermion. So that if you know the fermion, then you can build every material. Can you see? So why this, where does this strange name come from? Then that is where, because there's a famous Italian American physicist. His name is Fermi. You see? Can you make that? Because his contribution is very important. So therefore, this category of elements in standard model is called the fermion. So halfway, that is halfway about standard model now already. Any question? You may ask yourself, because you have another very important question you have to ask when you study this part is that why do we need these fermions, all of 24, all of them? Why do we need this fermion? So I tell you why. Okay, do you know the answer?
Because different particles are made up of it.
Yes, that's right. So they can by using this called this is so we can build other particles. Can you see? And I just put this particle here. Okay. In chemistry, right? We have these 3 elements, okay, which can be used to build everything. Okay. So one is electron. You see, electron. What's happened to my pen? Another is proton, right? Another is neutron. Okay. However, according to quark, for the standard models, electron is electron. Can you see? Electron still is a basic charge. Can you see? We got electron. Can you see? Electron is just elements of the standard model, one of elements. But for the proton, you have to be careful. I've never remember this order. Roughly, you have used 2 up and 1 down quarks. I'm right? I'm not sure. And it's other way around. So basically, for the neutron, we will see if we can build this one. Because for electron, for the proton, can we just prescribe show you how do you make a proton? You see, for the proton, what is the charge of proton? In term of the E, electric charge. What is charge of proton?
+1.
+1. What is the spin?
Half.
Half. Yes, you are right this time. Okay. So how can we possibly build this proton by using quarks? Given, I just write down here, this up quark, this down quark, all right? And for the up quark, I just wrote it before, the charge is positive, the positive 2/3, right? And the down quark is negative 1/3. And the spin is the same, can you see? Are they? Spin down quark, no, down quark, let's double check I put my glasses. Half, yes, spin is half. Okay. Now, if I say we use the 2 upper quark, which implied, is that right or wrong? If we use a 3 quark, so basically the charge, the total charge will equal to 2 quark. See, that is a 2, 3. I'm talking about charge, okay? Charge of proton. We know charge of proton. You see. Sorry, other way around. Let's just read this. I'm trying to use a simple relation. So for the proton, right? For the charge of proton, that's the way to go. And if I use 2 upper quark and 1 down quark, what would be the sum? The very simple math, the simple algebra. That's how they built a new particle by using quarks, by using elements. Can you see? Probably this is not right. Is that right? Take. Right. Do we get 1 or not? No, we don't.
That's 1/3.
Sorry.
It'll be 1/3.
If you use 2 up quark and down quark, can we build the charge with build proton whose charge is 1? No.
This is equal to 3.
Ah, it's not right. Oh, it's 3, 1/3. Okay. Oh, can we build that one?
Yes.
1, are you sure?
Mhm.
So we got 4/3, right? Take 1. Oh, yes, you're right. All right, we can build it. Can you see?
Yeah.
So that is how they build a proton. Can you see? Use quarks. Okay, give you another charge. Okay, another try. Charge of neutron. We know it is -0. How can we build this 0 charge? Yeah, that is how we use elements to build particles, which is not fundamental. Oh, it's good. Looks like that. Yes, that's how to build it. Okay.
Yeah.
And the trick is how to build. I forgot how to build the spin. All right, because they're both are half, so they have required that one spin is anti-parallel. Can you see? So what does it have in terms of spin? So there's a spin of either proton and neutron. So they have required, for example, up quark is a spin is positive. Can you see? So they have somehow to manage it to that. Okay. So basically we got this is a configuration, just like do you know the electron configuration in chemistry?
Yes.
Yes, so this is very similar. So if you put a 2 quark whose spin one positive half, you see, positive half, and the second one is upside down, so you can negative half. Oh no, they get 1. Something wrong. Anyway, this is question I don't know. I forgot how to explain, right? Because the spin of the proton is also the half. Never mind, at least we have solved this puzzle. How do we build the neutron and the proton? You see? And the other part
still be 1/2, won't it?
Sorry, 1/2. Yes, but they got a 3 1/2. Can you see? How can we justify? Oh yes, yes. We're right. Oh no. Oh yes, my algebra is terrible today. Can you see? It's cancelled, right? It's still half. Yeah, that's right. That's what I mean by using them into one of them is upside down. Okay, does it make sense now? Do you agree?
Yeah.
So that is that argument is say, well, you see, we can just invoke quarks, and all we can use to everything in chemistry. Okay, we can make all material more chemical. Can you see?
Yeah.
That's how they built the universe, the matter, by using quarks and electron. Okay. Of course, if the energy is increased, I just write down here. So if that is how this experiment, that's why they built the quark model. If we just use high energy to let two particles to collide, right? It's called head-on collision. It could be 2 protons, you see, okay, 2 positive charge, and the 2 proton is called head-on collision. Okay. The machine is called collider. It's actually an accelerator in Europe, in Geneva, Austria. And they got the whole 30, a small town rather. The diameter of the circle is as large as the whole town, right, underground. So they use a high power magnetic field to accelerate a positively charged proton and eventually let them collide, okay? If the energy is very high after the collision, they will see something, lot of phenomena. Can you imagine they collide, right? If energy is high, so basically they will generate what we call the particles of different kinds. Can you see? Some are still fraction of the proton, like quarks. Well, they hope, but unfortunately they haven't seen quark yet. But they just see lot of new particles. You see, this particle is called subatomic particle. That's right down here. It's called this particle generated by collision is called which means less than subatomic particle. There are many, hundreds of them, all right? But how many quark and lepton do we have? Do you remember? 12, right? If we don't consider their antimatter. So basically, E for energy. So E energy for acceleration, okay, used. That is what they argue. They want to increase energy used in the collider. It's called a collision, okay? Collision or the acceleration, accelerator. So basically, if the energy is low, for example, just a few MeV, all right? And we can only say in this case, we only say we're finite. We got a proton and neutron, okay? Proton and neutron. However, if the energy increase, you see, if the energy is, we can say lot of particles, you see.
Yeah.
And there are so many, okay, hundreds of them particles, right? And this is probably the maximum we can achieve at the moment by human. So we have seen a lot of things. Very recent one, we have the Higgs particle. Do you remember the Higgs particle? Have you heard of Higgs particle? Not yet.
No.
It's called a God particle. That's very attractive, right? Fancy word called God particle. God particle. Anyway, we're mentioning the Higgs particle later on. And among them, they have, say, the sigma particle. Okay, you have never heard of a sigma particle. Or sigma particle is something like they got different charge, different spin. So basically, all of these particles can be built by this fermion. Does that make sense now? In the same manner as we built proton and neutron. You see that?
Yeah.
So that's how the standard model was introduced to explain this so-called subatomic particle. Okay, of course, electron. We got electron, got proton. In chemistry, we at the most we can separate them. That's all, right? In chemistry, we barely. This is actually in chemistry we actually is talking about the molecule. Can you see? We start from molecule, right? Like CO2. Can you see? H2O. So what we study is the particle molecules, right? So this, if we go that far, this is atom. So this atom, right? In chemistry, we never pay attention to this subatomic particle. So this we are only study the molecules or compound, right? Molecules. Do you know why the people use a compound sometimes, molecule instead of molecule? Molecule. Do you know why do people call the molecule sometimes called compounds in chemistry?
Because the compound can have one or
Bonding.
two molecules in there, like multiple molecules.
No, the compound is made by ionic bonding, where a molecule is made by covalence. Is that right? Have you did the physics teacher tell you that? So basically, that is a question we need. So, for example, when we study a molecule, for example, we study the hydrogen and oxygen, right? We were trying to work out the chemical bond. Okay? Can I use a color? Can I use a red color? Because this invisible force, right, connect this molecule. It's called chemical bond, right? This chemical bond can be divided into ionic bond and a covalence bond. Okay.
Yeah.
Now, question arise: does any force between these quarks when they form the proton? Question. What do you think? Any bond, not chemical, but you can say quark bond. any bond exist?
I don't think so.
You don't so. If not, how can they move together? if how can they move? How could they move together? Especially you can see there are two positive quarks. Can you see? How could that happen? Can you see that? That is something we need to. Can you see how could these two positive quarks move together in order to form the proton? According to Coulomb law, do you still remember the Coulomb's law? The Coulomb's law says the force between the charge part, two charge positive is repulsive if their charge is identical, the sign is identical. So what would happen in that very tiny area? So this area is very close to 10 to power negative 15 meters. That is the distance. That is the size, or even smaller. That is approximately the size of proton, right? So without any bond, without any attractive force, how could we put the two positive charge together? Let's go to next page. So that is a challenging question. We have encountered this challenge before, you see. So that is a nuclear bond. So nuclear, when we study nuclear physics, nuclear binding force, they call it binding, same thing. Do you remember nuclear binding force or binding energy, this idea? You don't forget. For example, if you consider the helium nuclear, okay, so helium nuclear is just alpha particle. Do you agree?
Yeah.
Or alpha particle, or we have make into ion forms. Alpha particle is called helium nuclear. Okay. For the alpha particle, what does the nuclear looks like?
Two protons and two neutrons.
Yes, so we got two protons. Can we just enlarge that? We got two protons and two neutrons. Okay, and the neutron has no charge, so therefore there's no repulsive force, right? This nuclear of helium nuclear. However, for these two protons, the distance is so close. Can you see? I think we encountered this question. We encountered this trouble before when we start the nuclear model. Can you see? So these two distance is very close to 10 to power of negative 15. So therefore, the force, the Coulomb force, right? Can you use this? So the Coulomb force is repulsive. The Coulomb force, can we write the formula here? This force, F, a moment, is equal in magnitude, opposite. So the force will be K E squared, because charge is E for the proton, right? So this is proton, this is a proton, this is a proton. What happened to my pen? R squared. This force must be huge if I use the diagram to show you when the R equal to very small. You see that? So that is a force between these two. If I call this is a force, this is a force, and these are the distance. So this is distance between. So this is distance between the two protons. You see, 10 to power negative 15 meters. Okay. Now, can you work out the diagram for the force? It will increase, from very small to very, very large. Can you see? So, do you think the two protons can automatically stay together? Yes or no?
No.
No. That is why we need the very strong. There is yellow part. We use very strong force. We have to assume there's very strong force. I use yellow. Can you see? to hold them together. Can you see?
Mm-hmm.
So these yellow force, this is what I call the force which can attract the two proton is called a strong force, strong interaction.
Mm-hmm.
Or they call interaction, strong interaction. So this strong interaction must be attractive in order to overcome the repulsive force. Okay.
Mm-hmm.
So that interaction in standard model is described by a glue, a very strong glue, right?
Mm-hmm.
Because we prefer to use particle model, so that could glue on. Glue on, can you see?
Mm-hmm.
Another particle count called a glue on, right?
Yeah.
I think we have to get rid of E in order to make English correct. That's right. We have make this phonetic notation correct. We have to get rid of this E, all right?
Mm-hmm.
So the correct spelling of glue on. We know it's come from glue and on. So that's the written form is a glue on. You see? Glue for the glue, on for the particle. Okay.
Yeah.
So that is how to describe the force in standard model. So they assume that these two protons in this case, these two protons, right?
Mm-hmm.
They can exchange some particle. It's called this particle is called the gluon. I'm using this yellow one. Can you see that? Can you see the yellow could be here, could be here? They can exchange like a two-person play basketball. Can you see that?
Mm-hmm.
So that will create their attraction. Okay. So that is how they introduce a new type of particle now. Can you see? So this is a gluon. And this is proton. So these two proton. Of course, we know the proton inside they got up quarks. Can you see? And down and down. Can you see that? So basically, that is that's very strange, very abstract idea to describe the interaction between the proton. Can you see? It's called a strong interaction by exchange this particle called the gluon. Okay, it makes sense. Similarly, and when they look back, they say, well, what happened to the charge after all? Because if you have the proton and proton, you see. So if we just draw this one, so if you have the electron, can we just this time with two electron? We just consider two electron. This blue color, blue color to represent electron. So I'm trying to introduce idea how to use a particle to describe the interaction. Now these two electrons, because they are all positively charged, so therefore they have impulsive force, right? However, that impulse, how do we explain this force? We use Coulomb's law, right?
Yeah.
We use Coulomb's law. However, they say, well, forget about Coulomb force. We can introduce another idea to describe this interaction. So what do they do? They just create another particle. We know this name of particle. This is called the photon. Have you heard of photon? Can you see that? So what is a photon? So the photon is responsible for the interaction of two charged particles. In this case, two electrons. You see? So that is I write down here. So this electron, you see, we know it's repulsive. But instead of using Coulomb's law, they don't. They say, let's consider something other explanation. This Coulomb's law, they say we don't use Coulomb's law, we use gamma. What is gamma? Gamma is called a photon. You know when we study Einstein photon electron, we know what a photon is, right? Photon is a particle. So this is very important idea. So the force in the standard model is called the exchange particle, okay? Exchange by exchanging particles. The force, sorry. So force is equivalent to exchange, and exchange particles. Is that abstract idea?
So it's sort of like
yeah, force is not Newton's force, but now it's an exchange. Just like play basketball or netball. Do you play netball or basketball, volleyball?
So it's sort of like in chemistry.
Yeah, well,
they exchange like electrons.
Well, that is a physical part. It's not exchange. No, it's not. That we are talking about not exchanging matter, whereas exchange is interaction. So these particles may not visible. So imagine two players, the netball or basketball player, when they exchange the ball, basketball, right? You feel the repulse, both of them. Do you agree?
Yeah.
So that is how they describe the interaction in the subatomic world. Okay. How many interactions do we know in the universe, in the universe, according to physicists? 4. So four interactions. So there's basic force is called basic interaction. Okay. Have you heard of these 4 interactions? What are they? One is gravity. Gravity or gravitational? Gravitational. Gravity, we just call gravity. Like weight, okay, like the force between sun and earth. Another is called electromagnetic force. Electromagnetic. A third one is called a strong force. Okay, do you remember? Now we just talk about strong force. Okay, strong interaction. Another is called relatively weak interaction. And these two forces, so these two forces are short range. They only appear in a very short distance. Short range force, right? Short range. If the distance is large, these two forces disappear. So far, the standard model can use the same mathematical form or equation to describe the another three interaction. See, maybe I use a red color. So you see that? Now, I'm not talking about the matter. We're talking about the interaction or force now, all right? Because after all, if we got the matter, then if we know their interaction, then we can build everything. So that is the idea of standard model.
Yeah.
Okay? That could sound in Newton's mechanics, we call the force, right? Or even we use the electrical force before, right? So from point of view of physics, there are 4, but 3 of them, this gravity is relatively weak. So that is a non-range but weak. There can be this non-range force, but very weak. Okay, too weak, but weak compared with others. Too weak. Two. Okay, can you follow me?
Yeah.
I tell you the long story, but very briefly. So far in electromagnetic fraction, so how do we define this force? What particle do we use? We use a photon. You see? Do you remember? We use a photon. Used by this notation. How do we just describe the strong force I just mentioned? How do we describe the force? We use a glue, very strong glue. What is the name?
Gluons.
Gluon, yes. How we denote that? Can we use G? G for gluon, okay. Now, to cut the story short, there are two types of particles responsible for the weak interaction. One is W, okay, another is Z particle, all right? So this just interaction for these three, but so far there's no, it's impossible. So far they still dream that one day they can also use this description to describe the gravity, but unfortunately it is almost impossible, right? Now here I give you another type of particle in standard model. So all of these exchange particle responsible for different fundamental interaction is called, can you guess what is the name? BOSON, okay? Some people pronounce as boson. Some people pronounce as boson because correct English pronunciation. However, both are correct because this BOS come from the India physicist whose name is Bose. Okay. So both are correct. So that is a boson. That is a boson. So boson is a particle of this group. Can you see? All of them is called boson. If I just highlight that, which represent the interaction, the three fundamental, you can put boson. Okay. That's it. That is almost all particle we're going to learn in the standard model. Another one is called the Higgs particle. Okay. That is a hypothesis in 1960s. Recently, a few years ago, they claimed that they have experimentally discovered the Higgs particle. Higgs is a physicist, okay, who put forward this idea first in 1964, 63, for the Higgs particle. So Higgs just the surname. So what is Higgs particle? Because so far, if I put all these particles together, can you see? Can I write the particle now? U, D, and charm, strange. I write quark first. Top and down, top and bottom, right? And then you got electron and neutrino, electron, neutrino. They got muon. They got neutrino, muon type neutrino. That's lepton. That is a tau particle. So both electron, this group have similar mass, but they are much less than quark's mass. So that's why they called lepton. Lepton means, so this is lepton, do you agree? So this I just group thing. This is called lepton, and this is called quark. Is the quarks? Can you see? So this group is called lepton. Write down properly. Lepton. Lepton means lighter particle compared with quarks. Lighter. GHTER. Lighter particle, all right? Lepton means lighter particle. Here we need almost finish all. And these are called quarks, okay? Quarks, 6 of them. If you multiply, they have anti-quarks. And now, do you remember how do we call this particle? All of them. What is the category we used?
Fermion.
Fermion, yes, fermion. So this is called a fermion. Yeah, so that's due to the Italian-American physicist called the fermion. It's called a fermion. Fermion, all right? Now, let's just put what we have learned here. For the strong interaction, we got glue, right?
Gluon.
For the electronuclear interaction, we got gamma. We put it this way. So we got electro magnetic interaction. We got a strong, we got weak. Okay. For the electrostatic with photon, can you see? Not this one, gamma with gamma, can you see? For the strong interaction with glue, we don't call it glue, we call it gluon, right? For the weak, we got two particles, W and Z particle. That's it, everything, except the Higgs particle is here. So then that is this answers this question. So what is a Higgs particle, and why they getting very excited when they say Higgs particle was observed? Because all of these particles except electron are mathematical elements, model in the mathematical model. These mathematical element called particle, but they don't have mass. That's the trouble, right? Even we say the electron, even we say the quark has, so quark's model, so his mass remains unexplained without the Higgs particle. Can you see?
Yeah.
So that is a big trouble before Higgs particle was observed. Together with Higgs particle, wow, they say they have found everything. You see? You see they have found this boson. Can you see? This purple line called boson. Can you see? Due to a boson, if you want to call the English correct, you can put boson. This boson. Can you see? Wow, that's the end of the story. Everything about the Standard Model. Any question?
No.
No, you can follow me today. Yes, that is non-journey, right? That's a non-stories, non-story. We build everything. Now we can build everything mathematically, at least, right?
Yeah.
Okay. See you next time.
Okay, I'll see you next week.
Okay.
Thank you.
You're welcome. Goodbye.